Morning, you are welcome back to the class. This will be the last class for me. And as you all know, we started the transition metal chemistry last week, Thursday. I hope to round up today. We earlier on told you that all are metallic and they possess strong metallic bonds. They lose electrons in the 4s orbital first before the 3d orbitals. And that account for their formation of various oxidation states. Now, let us look at oxidation states formed by these elements. Now, when 4s electron is lost, the two 4s electrons is lost, then you have a +2 oxidation state. As it is here, scandium is 21, then the 4s electrons, when they are lost, then it means scandium +2 has electronic configuration of a 3d1. So when the 4s electron is lost in titanium, then that means you have a titanium ion, titanium +2. The configuration is a 3d2, argon 3d2. So likewise, vanadium will be 3d3. Then chromium, 1s electrons of the 4s orbitals will go, then another one will go from the 3d. So chromium +2 will be 3d4. So you have all, apart from you have, when all two electrons are lost, then you can have titanium +2, vanadium +2, chromium +2, then manganese +2, then iron +2, up to copper +2. Okay, but when 3 electrons are lost, that is 2 from the s orbitals and 1 from the d orbitals, making 3d electrons. So that will give you +3 oxidation states. +3 oxidation states. Now, scandium +3, then that means all the 3 electrons of the 4s, the 4s and 3d orbitals, all the 3 electrons are gone. So scandium +3, we have a 3d0, 3d0, or 3d0, as the case may be. Okay, so +4 oxidation state is formed by losing of 4 electrons, and +5 oxidation state is formed by losing all 5 electrons. Now, if you take a vanadium, for instance, when all the 5 electrons are gone, when all the 5 electrons are lost, then vanadium +5 will have a D0 configuration. In other words, there can be no transition of electrons from the ground state to the excited state. Hence, vanadium +5 is colorless. Vanadium +5 is colorless. So any ions with D0 configuration or D10 configurations, they are all colorless. we spoke about the shapes earlier. Then coordination number, we've spoken about that. The ligands, naming of complexes. Still naming of complexes. Yes. Now, coordination compounds or whatever, or complexes. Now, example you are having here, you have a coordination compound, K3FeCN6. So, which we call the potassium is the cation, then the anion altogether is the cyanoferrite 3. So, because we have coordination compounds, we have a cationic complex, we have neutral complex, then we have an anionic complex. So this compound is named potassium hexacyanoferrite 3. Why is it ferrite 3? I told you that once you have a negative sign, or a negatively charged complex, you end it with 8. If it is vanadium, then it ends with vanadate. If it is copper, then it ends with cuprate. If it is zinc, then it ends with zincate. So now the second one, this is a diamine difluoroplatinum 2. Diamine difluoroplatinum 2. You have how many ligands? How many ammonia? You have 2. 2 ammonia ligands. Then you have 2 fluoride ligands. Remember that ammonia is named amine, then fluoride is named fluoro, and A comes before F. So diamine, difluoro, then the metal oxidation state is +2. So diamine difluoroplatinum 2. Diamine difluoroplatinum 2. Then the third one, this one is tetra-aqua dichlorochromium 3 chloride. Now, the green chlorine satisfies the primary valency. Then the blue chlorine is inside the coordination sphere, satisfying the secondary valency. So, and in naming this compound, water, which is aqua, A comes first, then followed by C, then the last one. So now we have 4 water, tetra, 4 water, that is tetra water, or you call it tetra aqua. Then how many chlorines do we have inside the coordination sphere? That is two chlorine. So tetra aqua dichlorochromium 3, then chloride. Don't forget that the oxidation number of chromium here is +3. How do you calculate? How do you get +3? The sum of oxidation number of all elements in a compound is equal to what? Equal to 0. The sum of oxidation number of all the elements in the compound is equal to 0. Now leave chromium alone. Water is neutral. The oxidation number is 0. Okay, and element of group 7 has oxidation number of -1. So if you pick up this -1 times 2, that's 2, -2. Then there is another -1 outside. So making -2 plus -1, making -3. So that will be if the oxidation number of chromium is X, That will give you x plus 0 minus 2 minus 1 is totaling equal to 0. So in other words, you have x minus 3 equal to 0 and x equal to plus 3. So now if you remove the green chlorine here, then this complex will become positively charged. It will become positively charged. That is, you have the cation and the anion. If you dissolve it in solution, you have the chromium, the tetra-aqua dichlorochromium 3 ion in solution, as well as the chloride ion, ion in as anion in solution as well. So catalysis. Now, example of catalysis: oxidation of SO2 in the contact process is catalyzed by vanadium 5 oxide. In step 1, what is catalysis, by the way? How do you catalyze? Catalysts are agents that increases the rate of reaction, while inhibitors reduces the rate of reaction. So the rate of chemical reaction here is enhanced using vanadium 5 oxide. In step 1, the vanadium pentoxide react with SO2 to give you V2O4 plus SO3 in the first step. So in the second step, you have the V2O4 plus oxygen to give you back V2O5, meaning that your catalyst, you must have your catalyst back at the end of the reaction. The overall reaction now, because you have this catalyst, can't catalyst, then you have S2O4 plus oxygen to give you SO3 solid. Magnetic properties. This is the ability of transition metals to either attract magnet or repel magnet, or not even attract at all. So, and these are in 3 places. 1, paramagnetism. 2, diamagnetism. And the third one, ferromagnetism. Now, let's look at paramagnetism. These magnetic lines of force pass through the substance rather than through a vacuum. The magnetic lines of force pass through the substance rather than through a vacuum. So paramagnetic substance is attracted into a magnetic field, and this is majorly caused by the presence of unpaired electrons. Now, when you have electrons, singly occupied orbitals, then it means that substance is what is paramagnetic. The extent of paramagnetism varies. 1 electron is less paramagnetic than 2 unpaired electrons, and 2 unpaired electron is less paramagnetic than 3, and so on. So all the d orbitals, 1 electrons, 2 electrons, 3 electrons, 3 electrons, 4 electrons, 5 electrons, all unpaired, then everything, like all substances with unpaired electrons are paramagnetic. They are paramagnetic. However, we can have diamagnetism, in which case, when the electrons are paired. So magnetic lines of force pass through the vacuum rather than the substance. Remember, magnetic lines of force pass through the substance rather than a vacuum. That is in paramagnetic. But in diamagnetic, the magnetic lines of force pass through the vacuum rather than the substance. Thus, any diamagnetic substance will be repelled by a magnetic field, and hence tend to set itself at right angles to the field. All electrons are paired. Now, paramagnetic, unpaired electrons, diamagnetic, paired electrons. Paired electron. There's another situation called ferromagnetism. This is a form of paramagnetism, but the moment on individual atoms become aligned and all points in the same direction. Substances, they are a kind of paramagnetic substances whose moments on individual atoms become aligned and all points in the same direction. Example of ferromagnetic substances, they are the iron, the cobalt, and nickel. Iron, cobalt, and nickel are very well-known example of ferromagnetic substances. Oh, very good. So, in other words, we have come to the end of this lecture. But let me go right again. What will happen? So I just want to revise transition methods. I'll just rush through. So the periodic table is divided into 4. The s orbitals, the p orbitals, the d orbitals, and the f orbitals. So s orbitals, all elements with 1 electron or 2 electrons in the s orbitals, they are referred to as s block elements, particularly group 1 and 2. From group 13 to 17, they are the p orbitals because the electrons are in the p orbitals. Whether you have a p1, p2, p3, p4, p5, p6, up to that's group 18, p6. So you will recollect that group 16 and 17, 16 has 4 electrons in the p orbitals, while group 17 has 5 electrons in the p orbitals. In between group 2 and 13 are the transition metals or transition series comprises of each triad. So starting then titanium, zirconium, and hafnium, vanadium, niobium, and tantalium. So you have chromium, number 6 here, chromium, molybdenum, and tungsten. So you have manganese, titanium, and rhenium. While in 8, the iron, ruthenium, and osmium. 9 here, you have cobalt, rhodium, and iridium. Number 10, nickel, palladium, and platinum. 11, copper, silver, and gold. So 12 here, zinc, cadmium, and mercury. So Now, the electronic configuration of these elements follow the same trend. So, follow the same trend. We have some others that are called inner transition elements, but we are not going into that at your level. So, electronic configuration that has been explained. Argon first, 18, that's 18 electrons. For instance, after argon, scandium has a 3 additional electron. Argon, then 4s2, 3d1, making what? Making 21. So for 22 titanium, argon 4s2, 3d2, and so on. Only when you get to chromium, because of extra stability, adheres to 4s1 and 3d5. So that is why in chromium you have 4s1, 3d5, because chromium with this electronic configuration is more stable than the d4s2. Likewise, in copper, completely filled d orbitals is more stable than partially filled d orbitals. That is why you have, instead of having d8 s2 in copper, you have d10 s1. So 3d10 4s1, because of additional stability with half filled orbitals in chromium and additional stability with completely filled d orbitals in copper. So we say that they are all metals. They possess strong metallic bonds, lose electrons in 4s orbitals first. And when 2 electrons in the 4s orbitals are lost, you have a +2 oxidation state. +2 oxidation state. Albeit 2 electrons in the s orbitals are lost. 1 electron again in the d orbital is lost. Then that will give you +3 oxidation state. So now what we are saying in essence is that if we ask you, what is the electronic configuration of manganese 7? What is the electronic configuration of manganese 7? Manganese is 25 electrons, right? Manganese, 25 electrons. So manganese 7 means 7 electrons has been lost. 7 electrons have been lost. So manganese 7, that means you don't have electrons in the 4s orbital, and you don't have the 5 electrons again in the 3d orbitals. So the electronic configuration of manganese 7 is argon. Is argon configuration, that is 18 electrons. So, and it is written as 3d to the superscript of 0. 3d to the superscript of 0. So, I see here oxidation state. See manganese 7. Manganese 7, that means all the 7 electrons have been lost. Although it is supposed to be colorless, you have a potassium permanganate is a purple. That is due to charge transfer from the oxygen to the manganese. So color. So earlier we have explained color that you have the splitting of the d orbitals in the presence of ligand. For instance, you have in an octahedral environment, the d orbital is split into two, the Eg and the T2G. So, and the T2G is of lower energy. The T2G is of lower energy, while the Eg is of higher energy. The energy splitting, the crystal field splitting, is known as delta. So now an electrons will move from the T2G orbital to the Eg orbital. That is by absorbing radiations, by absorbing light radiations. Electrons move from the T2G orbital to Eg orbital. So, complexes and ligands. I think you are familiar with all this. If you start with anything, IDE will end with O. Anything, water is water, water is aqua, ammonia is amine. So you have a monodentate ligand, e.g., water, ammonia, then all the halogens, they are all monodentate. So oxalate, for instance, is a bidentate ligand. You can see is a bidentate ligand. Then ethylene diamine is also a bidentate ligand. Shapes. The shapes of complexes are governed by the number of ligands around the central metal ion. And this is based on electron pair repulsion theory. So if you change the ligand, then the shape can change as well. Don't worry, the slide will give you the slide, and I'll provide you with a note. At the end of today's lecture, you have all the notes and you have the slide as well. Okay? Okay. So we said the shapes are governed by the number of ligands. When you have two ligands that donate electron pair to the central metal ion, then the shape is linear. Linear. So linear. Okay. When four ligands surrounds the central metal ion, then the shape is either tetrahedral or square planar, depending on the strength of the ligand. So, for instance, here, depending on the strength of the ligand. Now, chlorine is a weak ligand, so it forms a tetrahedral complex with a copper. So the name of this, as you know, we have how many chlorine atoms? We have four. Four is what? Tetra. So tetrachloro cuprate 2 ion. This tetrahedral copper is tetrachlorocuprate 2 ion. The square planar nickel is tetracyanonickelate 2 ion. Nickelate 2 ion. Now look at the two-fold silver. This one is diamine silver 1 ion. Silver 1 ion. Why did that? Okay. But this is not minus. If this were to be minus, it will be argentate. Argentate. Remember, the Latin name for silver is argentum. So it will be argentate. But because it is positive, the charge on it is positive, it is diamine silver 1 ion. Now, you go to the sixfold. For instance, this is Cu. This is how many water do we have here? There are 6. So 6 is what? Hexa. So hexa aqua, then copper 2 ion. Copper 2 ion. Why is it copper 2 ion? How do you know that the copper here is +2? Like I told you, the sum of oxidation number of all the elements is equal to the charge on the complex. This is this. The charge here is what? Is +2. So see, if Cu is X, but water is neutral, 0. So that will be X plus 0 equal to what? Equal to +2. So 0 is gone. So X is equal to +2. This is why we call it as an aqua copper 2 ion. Once it is charged, let the ion be there. Once it is charged, let the ion be pronounced. So you cannot, but at least, because you have 4 questions, I am going to give you about 10 questions, at least one from this naming, IUPAC naming. So that is International Union of Pure and Applied Chemistry System of naming. So at least one question from this, from IUPAC, System of Naming Coordination Compounds. And you have questions and a variable oxidation state as well. Then magnetic properties as well. There are questions. So they are things that you know. Just take your time, read them properly, so that you won't have problem. Yeah. You are familiar with the naming of complexes. So I told you that these complexes, coordination compound or coordination complexes. So you have, for instance, the number 1 here is a coordination compound. Okay? And mind you, if you have K4 here, if the compound is okay, K4 FeCN bracket 6 as it is written. If you have K4, then the oxidation number of ion here will be +2. Will be +2 if you have K4 instead of K3. The oxidation number of ion here will be +2. So, and what do people call this can be called, you can call this one potassium ferricyanide, but in coordination chemistry, it is potassium hexacyanoferrate 3. But if K is instead of K3, you have K4, that will give you potassium hexacyanoferrate 2, what we refer to as a ferrocyanide. No, ferrocyanide is used in testing for iron 3. Okay? Then why ferrocyanide is used in testing for iron 2? You have in both cases, you have a very deep, blue, deep precipitate. So I told you that you have neutral ligands, we have neutral complexes, we have anionic complexes, then we have neutral complexes as well. So number 4 here is if the name of a ligand itself contains a Greek prefix. For example, you have ethylene diamine. There is already di in this complex. I mean, in the ligand. So if you now have a number of it again combine. I mean, donating electrons to the central metal. Then you can no longer, if you have to, you can no longer say diethylene diamine. That is wrong. Diethylene diamine, because the di is already in the ethylene diamine. Then you have another way of saying it. Instead of diethylene diamine, you have bis, by 2. If it is 3, you have tris. If it is 4, you have tetrakis. If it is 5, you have pentakis. And if it is 6, you have hexakis, and so on. Thus, this name here, because you already have ethylene diamine here, you cannot say triethylene diamine. You can't say triethylene diamine. So you just simply say tris, 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 then ethylene diamine in bracket. Then you have cobalt 3 chloride. Why is it cobalt 3 chloride? The oxidation number of cobalt here is +3. Now, if you remove the chlorine here, what will be the name? It is simply tris ethylene diamine cobalt 3 ion. That is if the Cl3 is not there. It is tris ethylene diamine cobalt 3 ion. So use a Roman numeral in parentheses immediately following the name of the metal to indicate the metal oxidation state. If the metal oxidation state is wrong, then you can't get, nobody will give you that answer. Of course, your question is MCQ. So if you any error, then that's the end of it. You can't get the answer once you make an error. So it is important that you study these things carefully. If it is not clear to you, let us know. So we'll provide you with notes with which you can read. Apart from the slide, the notes will come either before the end of today. So So I told you when you have anionic complexes, the name ends with AT. When the complex is negatively charged, name end with AT. You saw the example of where I mentioned cuprate, where I mentioned the nickelate. Then if it is chromium, it is chromate, and so on. If it is cobalt, it is cobaltate. If it is zinc, it is zincate. Zincate. So any once there is negatively charged complex, then it is it is named ate, ATE at the suffix. So yeah, gone through this. So àdúpẹ́ jẹ́ fún ní talk code D L H 3H. Okay. Yeah, it's okay, fine. The CN is an error, it's copper, please. It's copper. Fine. Yeah. Good. Thank you. That's catalysis. A number of transition elements, they act as catalysts for a number of reactions. In this case, vanadium 5 oxide or vanadium pentoxide. So converts SO2 into SO3. Nickel, finely divided nickel will give you, I mean, it's used in hydrogenation, okay? And finely divided iron is used in the EBA process for the production of ammonia. So a number of transition metals, they are good catalysts for various reactions. Magnetic properties. Again, we are talking about paramagnetism that is due to number of unpaired electrons. The electron must not pair, unpaired electrons. Diamagnetism, electrons must be paired. Ferromagnetism is a kind of paramagnetic properties, okay, but mostly displayed by iron, cobalt, and nickel. So if we tell you which of the following is not ferromagnetic, and you have vanadium there, you have you have copper there, we have four options. Just know that iron, cobalt, nickel, and ferromagnetic. Anything outside it is not ferromagnetic. First code has gone long ago. First code get you don't want first code to see. I'm giving the third code now. So all said and done, wait for your slides, then wait for your note. So before the end of the day, your note and the slides will be passed on to you. So if you have more questions, feel free to ask. Feel free to ask. Okay? Tomorrow, another lecturer will be coming in. That's the aspect of food. The aspect of food. Okay? So all the best with your exams. Thank you and God bless you. This is 8:50. Thank you. Àti ṣetán, ẹ káàárọ̀. Báwo? Ṣé o?
Yeah, good morning, everyone. So welcome to Physics 102 class. Yeah, Chemistry 102 has ended. So we are starting with 102 class now. Yes, are you guys? So we are starting with 102. So if you're online, can you let me have your reaction, please? Okay. Good morning, everyone. Are you there, guys? Yeah, thank you, Adekunle. Never come, I did telepresence now. Eh? 9 to 10. Yeah, so I'm already out. Hmm? Hmm. Yes, it's with me. What's the one bag now? Come for the key. Okay. Yes. Yeah, sorry guys. Good morning. Yes. Yeah, thank you. Olariwaju. So we're starting our class right away. Okay. So let's look at the recap of what we had on Friday. So we started with simple circuits. We have 3 simple circuits. So we have purely resistive circuits, we have purely inductive, and we have purely capacitive. And you were made to understand, know how to differentiate between these circuits, that in a purely resistive circuit, that the current and voltage are in phase. That is, the phase constant is 0. So that's how to differentiate the purely resistive circuit. For purely inductive, so you are made to understand that voltage leads current. That is, VL is greater than IL, or current lags voltage in purely inductive. So, and in purely capacitive circuit, that current leads voltage by 90 degree. That's pi over 2 radian. Okay, that IC is greater. IC is greater than VC. So in purely resistive, IR is equal to VR. IR is equal to VR. Can you hear me, please? Class, can you hear me? Please indicate if you can hear me. Hello? Can you hear me? Okay, thank you, Abolaji. So let's continue. So in a purely resistive, IR is equal to VR. Also in a purely inductive, VL is greater than IL. Though in a purely capacitive circuit, IC is greater than VC. So you can refer to this figure. Okay. Now let us briefly look at this question. We were unable to solve the question last Friday. So we're going to start from here. So the question said an AC generator has EMF, the EMF is given in terms of as a function of time. So the EMF is given as a function of time. Okay. And also it has this current. The current produced by that EM, okay, is given as a function of time. So K6 sub M is 30 volts and omega D is 350 radian per second. And I, that is the current amplitude, is 620 milliampere. So the first question is where to find after time t, the time that the generator will reach a maximum EMF. And also we want to find the time after t equals to 0 that the current will reach its first maximum. Also, we have to justify, so we're made to understand that the circuit contains another element. So you want to know the elements, okay, contained by that circuit. So we want to know if the circuit is purely capacitive, inductive, or resistive. So lastly, we now find if it is purely capacitive, so we find the capacitance of the circuit. If the circuit is purely inductive, so we find the inductance. And if the circuit is purely resistive, so we find the resistance. Okay, so let's solve the question together. Let's solve the question together. So we'll look at the solution. So we'll look at the parameters given. So the given parameters. So we have EM sine. So let me just write out the parameters. So we have this, we are given this. So we want to look at the time it takes the circuit to reach its first maximum EMF. So if you look at the given function, so EMF will be maximum when this parameter, that is sine omega dt minus pi over 4, is equal to 1. If this parameter is 1, then you look at the EMF will be equal to EMF maximum. So what we need to do is to now substitute this. Okay, so we have sine omega dt minus pi over 4 is equal to 1. So we take the inverse of this. Okay, so we have omega dt minus pi over 4 is equal to arcsine 1. Arcsine 1. In radian, arcsine 1 is equal to pi over 2. That is 90 degree. 90 degree. So if you take minus pi over 4 to this side, so we have omega dt will now be pi over 2 minus pi over 4, which is equal to a plus, rather, when you take minus to this side, you have plus. So this will be 3 pi over 4. Okay, make it the subject of the equation. So this will be 3 pi over 4 divided by omega d. So substitute the value. So 3 over 4 times 1 over, the value of omega d is 350. Okay, if pi is 22 over 7, okay, you can use your calculator, multiply 3 by pi by 3.142 or 22 over 7 and divide by 4 and multiply by 1 over 350. So the result will be 0.00673 seconds, or can write this to be microseconds. So 0.00673 or 6.73 microseconds. The topic, Abiola Babalola, the topic is alternating current. So it means you have not been following, okay, the class. Maybe you didn't even attend the previous classes. Okay, so we started with electromagnetic oscillations, then AC. So we are looking at AC. So we are now looking at series LC circuits. Series LC circuit. So this is the solution. Okay, that is solution for A part. Okay, now for B part, the B part, and now B part we are asked to find the current, that is the time that the current is maximum. Okay, so we use the same method. The current with maximum when this parameter, that is sine omega dt minus 3 pi over 4, when it is equal to 1. Okay, when sine omega dt minus 3 pi over 4 is equal to 1. So we have omega dt minus 3 pi over 4 is equal to pi over 2. So you have omega dt is equal to pi over 2 plus 3 pi over 4. And this will be 5 pi over 4. So we have t is equal to 5 pi over 4 times 1 over omega d. And this will be 5 pi over 4 times 1 over 350. And this will give you 0.1122 seconds, or 11.22 milliseconds. Okay, so that's the second aspect. Now the third aspect, C. The question we have to set: the circuit contains a single element other than the generator. So is it a capacitor, an inductor, or a resistor? So we want to know. Now, to get this, what we're going to do is to find the phase difference. We find the phase difference. Okay? Now, if you compare the two, that is the EMF and the current, so we find the phase constant for EMF. So let's denote that one with E, and is equal to, this is minus pi over 2. The phase constant for the current is minus 3 pi over 4. So let us find the phase difference, that is phi current minus the EMF, and this will be minus 3 pi over 4 minus pi over 4, and this will give us minus pi over 2. Minus pi over 2. The phase difference is minus pi over 2. So what does this inform? It informs that current lags the voltage by 90 degrees. And in that case, the circuit is what? Is purely inductive. The circuit is purely inductive. That is, it contains the generator and an inductor. So it's purely inductive because current lags voltage by 90 by pi over 2. So here, current lags voltage by pi over 2. So the circuit is purely inductive. Then the last part, okay, if it is purely inductive, so we're going to find the inductance. Now, to get the inductance, what you need to do is to just relate. So you can do this one, okay? Do this one by yourself. Relate. So let me just give you the clue, okay, for the aspect. So we have EMF is equal to IX EMF is equal to IXL. EMF is equal to IXL. So here, your I, the value is given, that's 620 milliampere. E is given also, E is 30. So if you make substitution, from there you get your XL. Then you recall that XL is equal to omega DL. Omega DL. So whatever value you obtain here, put it, okay, here, and put the value of omega D, and you get the value of L. Get the value of L. I think we are okay with this. So we continue with the rest of the class. So today we're looking at series RLC circuit. We started last Friday, so we just continue because we have looked at the three simple circuits. Okay, we have when we have the generator, okay, with either of these elements. That's the generator with resistance, generator with capacitance, generator with inductance. Okay, but today we want to look at when we have all the elements in the circuit. That is the generator, we have the resistance, we have the capacitance, and we have the inductance. Okay, now if you recall from equation 17, this is our equation 17. Equation 17. If you recall from this equation 17, that is the EMF, that's external EMF, is Kc is equal to Kc sub m sine omega dt. And we were made to understand that the EMF will drive. Deborah, can you please, maybe you should change your location because network is okay. So we don't have any problem with the network. So can you please, maybe you should try and change your location. Okay, Deborah Olawuni, can you please kindly change your location because network is okay. Okay, now if you recall from equation 17, so the external EMF is giving us this, and we are made to understand that that external EMF will drive the current along the path, and that the driving current is giving us this equation. That's the previous equation, equation 18, if you can recall, that I is equal to I sine omega dt minus phi. Now, for RLC circuit, Fumilayo Mercy, forget about the slide. Pay attention. Make sure you focus and gain something. There are so many things that will not be in the slide that you are going to be giving in this class. Why can't you just focus now? Later release the slide. Now let me give the first code. Let me give the first code because I know some of you, what you are particular about is the code. So let me give you the first code. That's the first attendance code. Now the first attendance code is D2S23. D2S23. That's the first attendance code. Yes, so let's continue with the class. Set the current amplitude. That is the current amplitude. That's the maximum displacement above the mean point. The maximum displacement above the mean point. Excuse me, 1 minute, please. I don't know what happened. I just checked it on. I didn't see anything. Thank you, sir. Thank you. So the current amplitude is given by this equation. Okay? I is equal to KCM over square root R squared plus XL minus XC squared. Now, this R square root R squared, that is this parameter, this R root R squared plus XL minus XC squared is known as the impedance of the circuit. Impedance is the total opposition to an AC, that is the alternating current, the total opposition. So that is the impedance. So it's the impedance of this circuit. That's Z is equal to square root R squared plus XL minus XC squared. So if from the previous slide, previous classes, you are given XL as a inductive reactance to be omega DL, and the capacitive reactance 1 over omega DC. Okay, so if we substitute omega DL for XL and 1 over omega DC for XC, so we have this equation. That's I, the current amplitude. So this equation is the current amplitude in an RLC circuit. Now, we need to find the phase constant of this circuit. If you recall from the previous classes here, so we're going to focus on this. We're going to focus on this figure B. Okay, if you look at this arrow, see the direction. So you see VC here. So this VC, it means that's when current leads the voltage. Okay, so this one is VL. That's when voltage leads the current for inductor. So this is for capacitance and this is inductor. Here, both current and voltage are in phase. Now, if you want to, this VL and VC, if you want to write it in vector form, because we were made to understand in the previous class that the phasor, look at the direction, it is anti-clockwise. So this will be positive and here will be negative. So this is minus and this is plus. So if you want to write this in vector notation, because they are along the same line, so we have V, it will give us VL minus VC. And that is what we have in equation, in figure D. Figure D. So we have figure D. So this is VL minus VC. Now this is VR. Okay. Now if you use Pythagoras theorem, or we want to use what's it called? Vector sum. Vector sum. So this will give us the impedance. Okay, to give us the impedance, we are dealing with the I, and but here it will give us the EMF. So we have it now. So we can now rewrite, or we can redraw. We can redraw this diagram. We can redraw this in this form. We can redraw it something like this. So we have this. So we have it like this. This is the phase constant. Okay. So this is VR. VR. So this is equal to, this side is equal to this side. So we have VL minus VC. So if you use trigonometric ratio, we have the ratio of opposite. This is the opposite to this angle. And this is the adjacent. Opposite, adjacent. So the ratio of the opposite to the adjacent is tan of that angle. That is the tangent of that angle. So the tangent will be VL minus VC, that is opposite, over VR. VL minus, that is where we have this. So tan phi is equal to VL minus VC over VR. So if you replace VL with IXL and VC with ISC and VR with IR, I is common if you bring out I. So we have I into bracket XL minus XC over IR. So this cancel this. So this gives us this. So we now have the phase constant. The phase constant is equal to tan phi XL minus XC over R. So I is maximum. So we're going to look at one phenomenon. If XC is equal to XL, what will happen? Because we know that if XC is greater than XL, or if LS is greater than XC, but if XC is equals to XL, what will happen? If XC, when XC is equal to XL, then we have maximum current in the circuit. Maximum current in the circuit when XL, that is capacitive reactance, is equal to inductive reactance. It means the phase angle is equal to 0, and the natural frequency will be very, very close to the driving angular frequency. And then we say that the circuit is at resonance. So at resonance, the omega D is equal to omega. And from your previous classes, you know that omega is 1 over root LC. Omega is 1 over root LC. So we can, if you can make L or C the subject of the equation here, all you need to do is to just take the square of both sides and rearrange. And also, you can rewrite omega, you can write it in terms of the driving frequency or the natural frequency. So omega in terms of natural frequency, that's 2 pi f. And this is equal to 2 pi fd. So you have 2 pi fd. Now we want to look at the power. Power in alternating current circuits. Don't forget in your previous classes that you were made to understand that the amplitude of voltage, or that's potential difference, the charge, and the current will not continue indefinitely. That with time is going to damp out because of the resistance. Because the resistance will convert the electromagnetic energy, you convert it to thermal energy. So this energy will dissipate in terms of that heat. Now, if we have an external, EMF that will make up this energy that is being lost, that the oscillation will continue. Okay, and from there we're able to know that okay, this EMF is giving us EM sin omega D, the driving current in terms of I and omega D, that's driving angular frequency. Then we move on, we look at the resonance, that is when Xc is equal to XL. Now, this energy that is the energy that is being lost. So we want to look at the rate at which, that is the rate at which this energy is being lost. That is the power. So we want to look at the power in an alternating circuit. From the previous knowledge, you know that power is the rate at which work is being done. The rate at which work is being done, that is power. And in an electrical maybe circuit, power is equal to I squared R. That is the square of the current multiplied by the resistance. And from the previous equations, okay, that's from equation 18, if you recall, from equation 18, I is equal to I sine omega dt minus phi. So if you take the square of it and substitute it here, take the square of it and substitute it here, so we're going to have I sine omega dt minus phi raised to power 2. So if you remove the bracket, then we rearrange. So we have I squared R sine squared omega dt minus phi. Now, over one cycle, this is one cycle here. That's 2 pi. Over one cycle, the average value of sine, because over one cycle, theta is equal to 2 pi. Theta is equal to 2 pi. If you take your calculator and press sine 2 pi, 2 pi means 360 degrees. 360 degrees. If you take your calculator and press sine 360, it will give you 0. It will give you 0. So which means over one complete cycle, sine theta will be 0. It will be 0. So where theta is any variable is 0. It will be 0. Now, what are we now going to do from here, from what we have here? Okay, if you take the sine at 90, at theta equals pi over 2, sine theta is 1. At theta equals 270 degree, 270 degree, and that will be minus 3 pi over 2. Sine theta will give you minus 1. It will give you minus 1. But if you take the square of this minus 1, it will give you 1. So the square of that negative part, and that is why when you look at this, the second figure, this plot thing, look at it here. We don't have the negative side, unlike here. Look at the range here. Plus 1 to minus 1. That is the range of sine. Plus 1 to minus 1. But for sine square, because this negative, when you take the square of a negative number, it always gives you a positive number. So the sine squared will range from plus 1 to 0. So you can see plus 1 to 0. So the average value of sine squared is half. So here we can now rewrite power. We write power as I squared R over 2, because the whole of this, that is sine squared omega dt minus phi is half. That's the average value. Okay, so if you replace this with half, then this equation will be reduced to this. The equation will be reduced to this. Now, mind you, from indices, all of indices, we can also express 2 as power of this. You can rewrite 2 as this. 2 is equal to square root of 2 raised to power 2. So if you substitute this here, so we have I squared over root 2 squared. If you recall the law of indices, your O-level mathematics, then we can rewrite this as what? As I over root 2. You put everything in one bracket like this. Okay? So we can now rewrite this as this. We rewrite it as this. Now, what we have inside the bracket, that is I over root 2. What we have when we have what we have inside the bracket, I over root 2, is called IRMS, root mean square. Root mean square. So the current root mean square is I over root 2. So if we now replace 1 over root 2 with IRMS, we can now rewrite the average power. We rewrite it as IRMS squared times R. Also, we can define the voltage RMS. Okay, you can define it as V over root 2, and also the EMS, that's the EMS RMS, we can define it as EMS over root 2. So in a series RLC circuit, the average power of the generator is equal to the production rate of thermal energy in the resistor. And this is given as this: P average is equal to EMS RMS multiplied by IRMS cos phi. Now, since cos phi is equal to R over Z, that is resistance over impedance. Cos phi is equal to resistance over impedance. R is equal to resistance over impedance. So we can rewrite this here. Here, we can rewrite it as P average I squared R, or I or E squared over Z squared R. So your P average can be I squared R. Okay, here, what we have here, okay, it can be this. But if you recall that cos phi is equal to R over Z. So if you now replace it here, replace cos phi with R over Z. So this will be, it will be EMX over Z squared R. Okay, so let's continue. Now I want to look at the last aspect of this of the AC, that's alternating current. Okay, so don't forget that the beauty of an AC is it can be controlled by a device. You have been taught that earlier. It can be controlled. You can step it up, you can step it down with the help of this device called the transformer. So in the figure, so this is a typical, okay, it's an ideal, we assume that it's an ideal form. Okay, so we have the iron core, this iron core, this is the iron core. So we have some wire that are wound around it. So we have this one. So this one that we have on this side is called the primary coil. The primary coil. And on this side of it, we have the secondary coil. So if the primary coil is connected to the alternating, so it's connected to the alternating generator. Okay, so the secondary voltage and the primary voltage are related by this equation. So Vs is the secondary voltage and Vp is the primary voltage, and Ns is the number of turns. Okay, that's for the secondary, and Np, that's the number of turns for the primary. So we have this. So how can we now calculate the energy transfer? Now, one thing about this, if you want to step up a transformer, what you need to do is to increase the number of turns here. You increase Ns to step it up. To step it up, you increase Ns, so Ns will be more than Np. That's a step up transformer. But if Ns is less than Np, that is a step down transformer. Okay, so let us now look at, let me give the second code before we continue. The second code. So let me give the second code. The second code, P9CYF. P9CYF. That's the second code. Okay, thank you. Wisdom. Yes, P9CYF. Okay. So let's continue. Now I want to look at energy transfer. So the rate at which the generator transfer energy to the primary, that's the primary here, is equal to IV. Okay, that's current times voltage. So the rate at which the primary then transfer. So you have the generator transfer to this and this transfer to this. That's the secondary. Okay, and that is IV, that's ISVS. Now, because we are looking at an ideal, okay, ideal transformer. That is, we assume that the energy is conserved. Energy is conserved. No energy is lost. So energy is conserved. So which means the energy before the transmission must be equal to the energy after the transmission. Okay, so no energy is lost. So we have the conservation energy is now given as this: IPVP is equal to IS VS. So if you want to now find maybe you want to find the current in the secondary loop. So we have IS is equal to IP multiplied by NP over NS. And we want to find the equivalent resistance. The equivalent resistance is given at this equation. That's Req is equal to NP over NS squared times R. Okay? Tijani Adekunle Hakim, he said root mean square. What do you want? Now let's look at, now this, I have some questions for you that I want you to, on your own, to practice them, okay? Solve them on your own. But since we still have some time, so we still have like maybe 13 minutes, okay? So let's quickly look at the first one. I'll solve the first one, the first question. We'll solve the first question together. So the remaining questions on your own, so you should try and solve them, okay? Solve them and master them. That does not mean that what will come out in your exam, okay, will be this, no, okay? But something related, okay? Something related, okay, may come out because at least everything pertaining to what you have been taught. So, let's look at the first question. Say an air conditioner connected to a 120 VRMS AC line is equivalent to a 12.0 ohm resistance and 1.30 ohms inductive reactance in series. So we have to calculate the impedance of the air conditioner, and 2, the average rate at which energy is supplied to the appliance. Okay, so we want to calculate the impedance. We want to find the impedance. Now, the first thing that you need to understand is you must understand the given element. Okay, of a circuit. So here, what are the given elements? So we have this resistance, we have this inductive reactance. We have those two elements. So which question? Benga Daniel said the questions are blurry. Which one? What is not clear? Kuti. Okay, let me dictate the first question. Okay, let me dictate the first question. An air conditioner connected to a 120 volt RMS. It is clear. Okay, Fumilayo, thank you. Like Fumilayo has provided the solution to your problem. Daniel, so Fumilayo has provided solution to your problems. Okay, so the questions are clear. Okay, so I don't need to dictate them again. So the questions are clear. So maybe you should change the quality of the video. So change the video quality. Okay, now, so let us look at it. Look at the given elements. So we have the resistance, that is R, and we also have inductive reactance. There's no capacitive reactance. So we only have two elements. So if you want to solve this, the impedance will now be square root of R squared plus XL squared, because XC is 0. XC is 0. SC is 0. So SE is 0. So from here, all we need to do is to just put the given parameters. Okay. So resistance is 12. So we substitute. That's 12.0 squared plus inductive reactance 1.3. So 1.3 squared. So if you solve this, okay, so let's see. Let me use my. Okay. Now let me give the last code before we, because I don't. Last code. So that's GMGA5. GMGA5. So that's the last code. The last code, GMGA5. GMGA5. That's the last code. So let's find the (12.0) squared So 12.0, okay. So this will be 12.07 ohms. Okay. Now the second question said average rate at which energy is supplied to the appliance. So we have power is, you have P. P is equal to I RMS, that's RMS squared R. RMS squared R. And if you know that IRMS is equal to VRMS over R. So this will be 120. So P will now be V as, let me use it to be RMS squared over R. So and this will be 1.19 times 10 raised to 3 watt. So you were given this one before. EMS squared Z squared this R. So substitute the value. 120 for EMS is 120. No. So that's about that. Now before I call it a day. So let me remind you of your first tutorial questions. The set 1. Chapter 1, you were to provide solutions to question 1, question 5, and question 10. Chapter 2, solve question 1, question 3, question 6, and question 9. Chapter 3, solve question 1, question 6, and question 10. So if you are yet to get this, ensure you get it on time. Okay? So that'll be all for today. So our next class will be to come up on Wednesday by 12 noon. Attendance page is not opening. What could be the problem, sir?
Okay. I think that in general something.
Okay.
It's general. You will not be able to use.
I should repeat the question. Chapter 1, question 1, question 5 and 10. Chapter 2, question 1, 3, 6, and 9. Chapter 3, question 1, 6, and 10. Can we still get the manual? Yes, Benga Daniel, you can still get the tutorial booklet. Okay, so you can still get it. Go to Yellow House, go and get it, room G22. So you get it there. Thank you, sir.